Hello, I'm Arianna. As was just said, I'm one of the Intel and Lenovo sponsored PhD students. I'm in my first year with the Particle Physics department here at Imperial. So I'm going to talk to you guys about FastML on FPGAs for particle physics. So I develop accelerated machine learning models for the Large Hadron Collider at CERN. So I'm sure many people in here have heard of the Large Hadron Collider. It's a 27-kilometer long ring, as you can see on the map, that runs underneath Geneva. It's underground, and there are high-energy proton beams that collide into one another at about near the speed of light. And the protons are accelerated by superconducting magnets cooled by liquid helium down to minus 271 degrees Celsius, which is colder than outer space. And it's an amazing engineering feat that led to the discovery of a new particle called the Higgs boson back in 2012. So if you can see on the map there's a little label for CMS. That's one of the particle detectors, and that's the detector that I work on. You have a person in the middle there for scale. So this detector basically observes particles that scatter from the proton-proton collisions. The beam goes through the middle of this detector into the plane. So it aims to observe new particles and new physics phenomena and improve our understanding of fundamental physics. So more specifically, I work on the data acquisition side of the LHC. So how much data do we produce and process? This is a visual from 2021, so it's a little outdated now, but it gives you an idea. So YouTube's on there, generates about 300 petabytes per year of videos are uploaded. Netflix, 50,000 petabytes of streaming per year. Amazon Web Services, 500 exabytes per year of storage. And the Large Hadron Collider is up there at the top. It's sort of off the screen in gray. It generates about 40,000 exabytes per year of just raw data. So how can we deal with this vast quantity of data? So this is produced by about 40 million proton-proton collisions per second. And the detector that I work on produces 100 terabytes per second of raw data. Now, clearly, this is an unmanageable amount of raw data. This can't feasibly all be stored and analyzed. And therefore, we have a filtering system, which we call the trigger system. And it identifies only the interesting events and discards the vast bulk of the information. So we're looking for new physics, collisions that are exciting that we haven't seen before, and we want to discard everything that's boring that we've seen before. So we only keep 0.02% of events, but the decision has to be made within 12 microseconds, which is really not very long. So we need very, very fast ML algorithms to identify the interesting physics. So yes, ML algorithms are used extensively throughout the filtering system. And as I said, we only have 12 microseconds to do the filtering per event, and a huge quantity of data to deal with. So we have very high throughput and low latency. Current CPUs and GPUs are not fast enough. Their latency is too high. Therefore, we use a type of programmable circuit board called an FPGA. They're displayed here. In fact, the one on the left there is made at Imperial. It's one of the Serenity boards that goes into the LHC. So we use a software tool called HLS for ML to map the ML models that we make from Python onto FPGAs. And what my research is in is to develop, firstly, the ML models for real-time reconstruction of the proton-proton collisions. We also have to do neural network compression in order to make these models as lightweight as possible so they can run as fast as possible and be as computationally inexpensive as we can make them. And to highlight the collaborative work that we do with Intel, I'm also working on improving the OneAPI backend of the HLS for ML software to support the transformer architecture and also some compression techniques so that we can use them on Intel FPGAs that we have kindly been given by Intel to use at the department. Thank you very much.